Welcome to Sita Lakshmi Ramaswamy College. I'm Dr.S.Karthiga from Physics Department. So in this lecture video, I'm going to explain you about the basic mathematical tools that are useful for every physics student to understand their subject very well. So often in physics, we come across many derivations or many theoretical dealings of physical concepts. So to understand the theoretical part of the physics, you need to understand the mathematical tools very well so that you will understand what these mathematical expressions really mean or what we are doing actually. So this is the famous quote by the researchers uh, Bernard Russell and Galileo Galilei that the mathematics is a language or the important tool that is helpful in understanding science or this universe. Without mathematics, the understanding may not be easy or it is not possible. We could say it is not possible. So we can say mathematics is the language of physics. So if you become well versed in the language, you can shine very well in science. So in this perspective, the contents of this particular lecture videos are arranged in this way. So I'll explain you what is differentiation, when will we differentiate, and what is integration, dot product, cross product, and all. So I'll first explain you about the differentiation. So while doing your course on physics, you often come across the word the rate of change of temperature with respect to something, or the rate of change of position with respect to time, that is the velocity, and the rate of change of something. So we often measure the rate of change of a physical quantity with respect to some variable that may be time or that may be position. For example, I consider the rate of change of temperature, the physical quantity temperature with respect to time. So in that situation, what does that rate of change, the word rate of change actually means? What that actually measures? It actually measures how fast the temperature varies with respect to time. So how slow or how fast the temperature varies with respect to time, that is what the rate of change captures. So okay, rate of change does that one. So how will you measure it? How will you do that? So how will you make a reference? This is moving, this is varying fast, or this is varying slowly. So what will you do is, you will find the change in the temperature for unit time. So for unit time, how much variation in temperature occurs, this is your reference. So with this reference, so at all time or for different system, you will measure the temperature variation with respect to time. So for unit time, so this will make your reference. This will help you to identify whether the system temperature varies fast or very slowly. So this is your rate of change. So with this, for example, if I have del f is the variation in f of t, so maybe f represents the temperature, and for a variation of del t time, so then what would be the variation in f for unit time? So for del t time, we have variation del f. Then for unit time, so if you want to measure, what will you do? You will divide, you will make division. So you will have del f by del t. So we here plotted a function f of t. Here actually we have taken f of t as t cube e power minus t. So this function is plotted here. So you can find that we can consider this f of t as the position with respect to time. F represents position and t represents time. So the variation in position is shown by this graph. So we need to find the rate of change of f with respect to time. The rate of change of position with respect to time is nothing but your velocity. So uh, look at this figure, you can find the rate of change is not a single value for this complete path. It is varying, it is not constant, or it is not a single value for this complete path, because it is varying with respect to time. For example, it is the f of df by dt is something here, and it is different over here, and it is different at this point here. So if you want to make it more clear, here see, the function is actually increasing, but when you consider this part, the function is actually decreasing. So the rate of change is actually positive at this point, and the rate of change is actually negative at this point. So this makes clear that the rate of change is not constant throughout the path, it is varying at every instant. So if the rate of change varies at every instant, it is also necessary to calculate the rate of change at every instant, that is instantaneous rate of change. So how will you capture the instantaneous rate of change? So del f by del t helps us to find the variation in f for a short range of time, that is del t. So if you want to know the instantaneous rate of change, then you need to set del t to tends to 0, so that results in df by dt. So df by dt, the differentiation of f thus gives the instantaneous rate of change of the physical quantity. So obvious. So what is the differentiation mention? Differentiation helps to understand. It represents the instantaneous rate of change of the physical quantity with respect to the variable t, with respect to any variable, but in this case the instantaneous rate of change of f with respect to t. So with this, we'll say an example. So as I told, this f of t is nothing but, here I have plotted t cube e power minus t. I try to find the del f by del t at a point t equal to 1. So this is t equal to 1. So for that, I have considered a short range, that is del t equal to zero point 0.2, del t equal to zero point 0.2, and I found the del f over this point. So this is 0.52, this is 0.36, so that del f is 0.1526. So the del f by del t is merely 0.763. So when I consider del t to be 0.2, so that within the time limits 1.0 to 1.2, the system approximately has the velocity or rate of change of 0.763. So now I change del t to be smaller, so that del t is 0.01. Then in this case I found uh, the velocity to be 0.73. So it is obvious. So when you reduce the del t, you can get a more accurate value near 1.0. The aim for me is to find the uh, velocity at time t equal to 1. So I'm reducing del t more, so that I'll get I have reduced del t as 0.001. I got the velocity to be 0.736. So when I set del t to be 0, then it reduces to the differentiation. So you can find the difference from the differentiated expression. From the differentiated expression, substitute t equal to 1.0, then you will find the exact uh, rate of change at t equal to 1, that is nothing but 0.735759. So this makes you clear what does instantaneous rate of change mean. So also remember, while doing differentiation, df by dt is positive when the function increases, and df by dt is negative when the function decreases, and df by dt is 0 when the function doesn't increase, or neither increase or decrease, nor decrease. So even in this curve, we have plotted the points in which we have positive df by dt, and negative df by dt while switching over from positive to negative. So at this point the system have maxima. Actually at the maxima there is no variation in f for a few instant of for an instant of time. So at the maxima point df by dt is 0. So from positive to negative while moving, the system will take negative 0 velocity. So with this we now see the what does the integration represents. So as you have seen in your school studies or in school studies or some foundation course in calculus, you have come across that the integration means the area under the curve. That is, if you integrate the function f of t, then the integration represents the area under the curve which is plotted for f of t. For example, I have considered e power minus t here. The figure shows the plot of e power minus t. So the area under this curve f of t, this area under this curve, this area actually represents the uh, integrated value. So how will you represent integration? That is here I have represented it. That is integral t naught to t1 f of t dt is nothing but as limit t tends to 0, del t tends to 0, summation t naught to t1 f of t into del t. So let us now first with an example we'll try to understand what does this expression mean. How will it represent the area under the curve? So for example, consider the same integration expression. So first let us look upon what does this f of t into del t means. So consider the curve. So here I'll take t equal to some 1 or something, t equal to 1, and I have shown f of t at t equal to 1 is this length, and del t is nothing but this length. So when you multiply f of t into del t, then you will get the area of the rectangle with length f of t and breadth del t. So f of t and del t gives the area of the rectangle with length f of t and breadth del t. So next what you do, you sum it from t naught to t1 del f of t to del t. So from the lower limit to the upper limit, so you are making many rectangles and adding the area of the all the rectangles. So the sum f of t del t gives the sum of area of all the rectangles that I have shown here. So at the next step, after summing up, what will you do? You are taking the limit del t tends to 0. So let us see what happens when you set this del t length to be smaller. So here I have made the del t to be smaller. So with this you can see the selected area is actually is more or less matches with the area under the curve, so it fits with the curve. So when you make del t even more smaller, actually the even this is del t is not much smaller. So when you make del t tends to 0, even more and more smaller, then this area of the triangles, sorry, the area of the all the rectangles will perfectly match with the curve, so that the integration measures the area under the curve f of t. So with this we'll now look upon when will you use integration in physics. So obviously, for example, in calculating the mass of the system or the total charge of the system, where for example while calculating the mass of the system, the density of the system is known. That is, what do you mean by density? Density is nothing but you know the mass per unit volume, and you want to know the total mass of the system uh, contained in a volume V. So total to find, So you know the mass per unit volume, and you need to know the mass for the complete volume V. So in differentiation, you try to understand for the variation in F for unit change in T or something. So here, if you know for unit volume, you know the mass. So you want to know the mass for the complete volume V. So for that, what you are doing, so to find the total mass, you integrate rho into dV. So rho into dV. So this will give you the total, the sum of all masses contained in the complete volume. Okay. So in the similar way, if if you consider charge density also, so if the amount of charge present in a unit volume is rho of q1, then the total charge present in the complete volume can be calculated by integral rho as a function of q1 into d. So with this, we move on to the next part of this lecture video, that is on the vectors. So the vectors are equally important in physics. For example, when you consider the electric field, magnetic field on all, so the vectors are equally important. So we'll look upon the mathematical operations that are defined in vector calculus and the basic vector arithmetics. That is, firstly we look upon vector multiplication. So that particularly the dot product and cross products. So the dot product and cross products, we make multiplication among two vectors. So dot product results in a scalar output, and the cross product results in vector output. In the dot product, actually what you measure, you often say that you will measure how dot product measure how the two vectors are oriented to each other. So my question here is, the dot product does just measures how the how just measures how the two vectors are oriented to each other. It measures only the orientation of the vectors, or it measures something more than that. So I say it measures something more than that. So because let us see. So if you say that the dot product measure just uh, simply the orientation of the two vectors, then a dot b should be simply cos theta, but a dot b is not simply cos theta. This is mod a and mod b cos theta. So to understand what a dot product means, I wish you to first learn what is projection of a vector. So let me explain what is first projection of a on b first, that is, and projection of b on a. Then I'll come to the point what is dot product of a and b. So projection of a on b is, it actually means how much of a, the word please stress the word how much of a is pointing in the b direction, how much of a. So that does not only mean the orientation of a with respect to b, it also depends on the magnitude of a. So it is given here, that is mod a into cos theta. So a dot b hat, here I have given b hat because we are concerning only the direction of b vector. So that is the unit vector of b. We do not mind about the magnitude of b, so we just concern about the direction of b. So I represented here as a b hat. So a dot b hat is mod a cos theta, that is the magnitude of a and the orientation of a, how a vector is oriented with respect to b. So in a similar way, the projection of b on a is b dot a hat, that is mod b cos theta. So this represents how much of b vector is pointing in the direction of a vector. So now we come to the point, what does the a dot b represents. A dot b actually represents the projection of a on b into multiplied by the magnitude of B, or the projection of B on A multiplied by magnitude of A. So it not only depends on the orientation of A and B, it also depends on the magnitudes of A and B. So as dot product measures the orientation of the two vectors, so when the orientation of the two vectors, that is when the two vectors are parallel, the dot product would be maximum. When the two vectors are perpendicular to each other, then the dot product value is 0. So we'll come to the next product of vectors, that's cross product, which results in vector output. The cross product of A and B results in vector. So and it is quite different from dot product, that it is the cross product is maximum when the two vectors are perpendicular to each other, and the dot cross product is 0 when the two vectors are parallel to each other. So these are the contrast point between the dot product and the cross product. So as I've told, the cross product results in the vector. So A cross B is a vector. So if it is a vector, there will be two quantities, that is the vector has a magnitude as well as the direction. So the magnitude of the cross product, what it represents, and the direction of the cross product, what it is represents. This is the question. So A cross B, the magnitude of A cross B is nothing but the area of the parallelogram covered, spanned by the vectors A and B. So this would be the parallelogram formed by A and B. So this area is given by the cross product. So and the direction is obviously is perpendicular to A, both A and B. That is the plane the normal drawn for the plane containing A vector and B vector. So with this vector multiplication and all, we move on to vector differentiation or vector calculus. Firstly, we'll consider there are three types of vector differentiation. One is gradient, other is other is divergence, and the third is curl. First, considering the gradient, it actually deals with the scalar function. Gradient is the differentiation of a scalar function, and that results in a vector function. So and when you consider divergence, it actually the differentiation of a vector, and that results in a scalar. And when you consider a curl, it actually the differentiation of a vector, that results in a vector. So here the gradient is the differentiation of a scalar, that results in vector. So here the phi of x comma y is the scalar function that we consider, and the gradient of del phi is not a scalar, it is actually a vector. So the gradient is often used in physics. Actually, it has been used in three different ways. So let me explain you how these gradient can be used in your while using your physical problems. Firstly, the gradient represents particularly phi of I said gradient is taken for a scalar function. So the function varies. The scalar function varies with respect to x, y, and z. So what does this gradient, the vector gradient represent, is the direction in which the phi of x comma y z is varying fast. The direction in which the scalar function varies fast gives by it is given by the gradients. So the gradient gives the direction in which phi of x comma y varies fastly. Secondly, so it not only helps in finding the direction of fastest variation, but also using the directional derivative. That is, when you take del f dot when you take dot product of the considered if for example I want to find the variation of phi in a particular direction, then what you need to do is you have to find the unit vector along the direct in your concerned direction, and make dot product of the unit vector with del phi, then you will result in a directional derivative. This directional derivative helps you to understand how fast the phi is varying in that particular direction. So if you want to find the variation in particular direction, then also this gradient is useful. And the third application of gradient is very much interesting and very much important. So that is in finding the normal to the surface. For example, if I consider surface defined by phi of x comma y is equal to c, so this is the surface that I consider. I want to find the normal along the surface. So at each point, so it is a surface, so at each point you will have a normal. So if you want to find the normal to the surface, then del phi is the simplest way to find it. So del phi at each point represents the normal to the surface. So actually I have represented simply del phi. So you need to find the unit normal. If you want to find the unit normal vector, you need to divide it by the magnitude of the del phi. So del phi vector by mod del phi is the unit normal vector to the surface. So there are three applications. One is finding the fastest varying direction. Second, to find the variation in any direction. And third, to find the normal to the surface. So this explains the importance of gradient. So with this, now I move on to the divergence. Divergence, the word itself says why it has been used. It measures how much a vector field diverges or converges from a point. So this is what the divergence measures. It actually results in a scalar quantity. So this defines how much the vector field is diverges from actually the divergence is not for example, if you calculate divergence for f, it is not constant for the complete space. It actually varies with respect to x and y. For example, here I have given a vector field, so you can find the divergence is not constant throughout the vector field. It varies with respect to every position. For example, if you consider the center point, if you consider the center point, then you can find the field around the center point. So every vectors around the center point is moving outwards, so, or diverging from the center. So obviously at the center the divergence would be high compared to other points. For example, if I consider a point here, then you can find there are vectors moving towards and there are vectors that are moving outwards, so diverging from this point. So the divergence is positive, but it is small, quite small compared to the point at the center. So the divergence varies with respect to positions. So it is a measure how much the vector field diverges from the point you are making measurement. So at which point you are calculating divergence. So at the point you have to look upon how much the field are diverging from that point. Next thing that we need to understand is about curl. So actually in physics we come across many vector fields like electric fields, magnetic fields, and many of them. So often we need to understand whether these fields make the object whether these force fields make the object to rotate, whether they'll induce rotational motion or not. So in such a situation we'll use curl. So the curl is used to identify um, whether the object placed in that vector field experience a rotational motion. So if it's so, how fast it will rotate and about which axis it will rotate. That is what the curl gives. So del cross f is a vector, so whose magnitude the magnitude of del cross f is proportional to the speed of rotation. So for example, this is the vector field that I consider. So I place an object at the center for a there is no need that you need to place the object in the center. So you need to place the object at which point you want to measure. Suppose if I want to measure curl at this point, then I'll place my sphere over here and measure how fast the sphere rotates. Then that is represented by the magnitude of del cross F, and about which axis the sphere rotates, that represented by the direction of del cross F. So del cross F is 0 when the field is irrotational. So we move on to the vector integration. Firstly, see the line integration. So the line in what does the line integration measure? So that is nothing but integral f dot dr. Line integration represents f dot dr. So here the f vector is the concerned vector field, and dr vector is the direction of a tangent vector. So why actually what does this line integration measures is it measures how much the vector field f vector is aligned with respect to the curve. So this is what we measure. So how much the vector field is oriented with respect to the curve. So for that, how will you uh, how will you so we know the direction of f, and how will you set the direction of this curve? So or the path, this if I consider the object is moving, the system is moving from in this direction, how will you set the vector for this path? So that will be done by the tangent vector. So as you all know that the tangent is nothing but a tangent line, or tangent vector is nothing but the closest approximation of the curve using a line. So the tangent line is a line which approximates closely the curve. So we can to represent the direction of curve, I take tangent vector, and uh, I make dot product with the f vector, so that it gives uh, at each point it gives. For example, at point P, I find f vector, the orientation of I find the orientation of f vector with respect to dr vector, so that at this point it measures how much the vector field is oriented with respect to the curve. So in this way, I have to measure it in all points along the curve, and I have to sum it up. So that that will result in line integration. So in line integration, what you find, so you measure how much the vector field is oriented with respect to the path. So for example, when will you find line integration in physics? So for example, when you consider a force is applied to a system that is moving in along a path. So you need to make the system to move along the path. So I give a force. So if the applied force is oriented towards the path, then the work done will be very high. But if my force is not oriented to the direction of your path, then the work done along the direction would be very less. So this helps you to uh, so because of this reason, work done is represented by line integration. Work done is nothing but integral f into f dot dr vector. So the next thing we see is the surface integration. Actually, the surface integration calculate the flux coming out of a given surface. For example, if you consider a vector field or vector field, then you will find how much field lines cross the surface at a particular time. So how much field lines cross the surface, or if you consider a if you consider the dynamics of fluid, then you will measure how much amount of fluid coming out of the surface at a particular time. So this can be done by surface integration. For example, the surface integration is represented here. Here f dot n hat gives, so for if you consider a particular point, f dot n hat gives the normal component of f. So the normal component of f, so that it will give the amount of felines that comes out of the surface at that point. So if you find f dot n all the points on along the surface, then you will find the total flux along the surface. That is what you have done here. So you find f dot n and sum it up for all points over the surface. This is what the surface integration gives. So with this, I conclude my this lecture video. So I hope you all understood about the basic mathematical tools that are used in physics or science. So I hope this lecture video would be helpful for your studies. So thank you for your patience. Thank you so much.